My name is Clark Hathaway, and today I am presenting work I did with Sebastian Mobo at the University of Tennessee, Knoxville, with mentorship from Silvina Canalores, Travis Johnston, and Michaela Taufer. The title of our poster is A Framework for Linking Urban Traffic and Vehicle Emissions in Smart Cities. I'll start us off with the introduction at the top left corner of the poster. Traffic in big cities is something most people are already familiar with and would easily be described as both inefficient and a major cause of pollution. However, despite the obvious concerns of traffic congestion and the harm done to both public health and the environment by vehicle exhaust, the questions researchers ask in tackling these concerns do not come packaged with simple answers. The first question we ask is, what impacts on vehicle emissions do traffic patterns have, specifically the patterns we describe as congestion? If we can mitigate emissions by reducing congestion, how do we define and measure congestion itself? If vehicles are quite literally driven by human behavior and decision-making, how do we separate the impacts from human behavior and other, less obvious variables? And finally, how do we consider multiple data sets when they're diverse in both their formats and method in which they were sourced? In our exploration of this problem, we develop a methodology to understand the relationship between traffic patterns and emissions that can be generalized for future work. To test this methodology, we apply it to data describing the Chicago Loop, although with minor configuration, it can be used on similarly structured data for other regions. Moving along the top rows in the middle, we can see how our overall framework contributes to studying this problem, as it extrapolates and transforms non-spatial data into spatial data, fuses these new data with urban layout data, visualizes the distribution of traffic and emissions across space and time, allows us to extract meaningful correlations from these fused datasets, and is portable across many platforms, including Power9 systems. Moving down, we can look over our workflow to understand our methods, starting at the top level in blue. At this first level, we consider the datasets describing vehicle traces, building footprints, the road network, and emissions data. Moving down to the second level, we pre-process and simplify the data, or we correct any inaccurate vehicle positions by looking at the locations of road segments in the road network layout, and simplify detailed shapes of each building's base into bounding boxes and centroids to reduce computational load. Moving down to the third level, we apply two algorithms to extend and transform the data. The first algorithm maps vehicles to nearby buildings so that we have an approximation of traffic density per building. The second algorithm takes the emissions values that are given as one emission or heat quantity per road segment and computes their dispersal across the entire region of interest so we can better relate emissions to points with high traffic volumes. Below this on the fourth level, we can visualize the results of these algorithms to identify and qualify patterns we see in the data. Moving down to the fifth level, we aggregate the vehicle mappings per building by summing the mappings for each building to approximate traffic density, and we sum the emissions over the cross-sectional area of each building. At the next level, we investigate the correlation between traffic density and vehicle emissions, where these quantities are considered in a statistical analysis that quantifies the relationship between them for each building. On the right-hand side of the poster, at the upper corner, we present our results. If you're interested in getting a more in-depth understanding of what our analysis revealed, we encourage you to look over this section in more detail or refer to our extended abstract where we discuss these results. One clear result of this statistical approach is a weak positive correlation that exists between mapped vehicle counts and emission concentrations from 8 to 11 a.m. throughout the work week. At noon, this correlation is weaker but still significant. And finally, we take note that emissions levels drop by several orders of magnitude after midnight. Moving to the bottom left corner, we discuss the lessons we learned from this work and insights for future work. In applying our methods for characterizing, cleaning, and fusing data about traffic and emissions, we find a weak correlation between traffic and emissions during morning commute hours, and observe both spatial and temporal patterns in traffic emissions throughout the area of interest. We only considered emissions in one metric for traffic congestion, but future work could model other variables that affect emissions, such as building height, vehicle types, and weather, as well as develop other methods for relating vehicles to buildings, such as mapping vehicles to multiple buildings based on a distance threshold. If you would like to know more about our work, we again encourage you to revisit our poster or reference our extended abstract. Thank you for your time.